Okay, so this week we have the second seminar. So Stefan Weltge, who actually gave a talk, online talk 5 years ago.
Oh. Right.
Yes, right. Now this is the second talk, but now it's offline talk.
Yes.
Talk about relaxation, complexity, and some polytalk, right?
Thanks a lot. Yeah. Thanks a lot for attending. Thanks a lot for the opportunity to visit you guys here. It's been a lot of fun so far. So we already made some progress in research, so that was fun. But I also had the opportunity to explore Dijon and all its food options, thanks to Tony and Pascal. So that was really nice. So I'm having a great time. My main research interests are actually like at the intersection of combinatorial optimization and, let's say, polyhedral combinatorics, with a focus on the theory and linear programming. So we will see a little bit of this today. My plan for today is to talk about the notion that we call relaxation complexity, which probably you don't know yet. And so my plan is, in the first half of the talk, I will talk about some older result actually that serves as a motivation. And then in the second half of the talk, I will talk about some very recent result. So we found the proof for this only 2 weeks ago and uploaded the paper last week to archive. So you're the first ones who see a talk on this. If time admits, the general goal is to show you 2 proofs of 2 statements that I somehow like, and I hope you like too. Good. So we're starting from the following. So many problems, not all, but many problems in combinatorial optimization can be phrased as the maximization or minimization of a linear functional over a finite set of points. And mostly these points are 0, 1 points, or more generally, let's say, integer points. Okay? And so for instance, if you want, let's say we have a graph, just to fix some notation, suppose we have a graph, right? For instance, we might talk about the stable set problem. Then maybe the points we're talking about is you associate every stable set with its characteristic vector, which is usually a vector whose entries are indexed by the vertices, right? Or we might talk about, let's say, some other famous problem, let's say the traveling salesman problem. Then your Hamiltonian cycles will correspond to these objects. So they might be 0, 1 points indexed by the edges of your graph, right? And if we're already in this setting, then a typical approach to solve these problems, especially in practice, is to model them as integer programs, linear integer programs, which are of the type, well, you maximize or minimize, exactly this linear functional, right? But now you want to describe your set of points by, for instance, a system of linear inequalities in exactly these variables. And further, like if you just do this, that's what we call a linear program, right? But if you further restrict your variables to only attain integer values, then that's what we call an integer program, IP, right? And if you really want to make this work, let's say for any objective function, in the case of 0, 1 vectors, then this description of linear inequalities, it must satisfy that it exactly describes the set X. So by this I mean that the set of integer points that satisfy AX less or equal B should be exactly equal to X, right? So that this will work. Okay. By the way, whenever there is a question or you're confused, just let me know. Right? Good. So the main goal is to find an appropriate description of X, and once you have it, you can just go to your favorite integer programming solver, and hopefully it does the job, right? So let's like as a warm up, let's find such descriptions for these 2 sets, okay? So maybe stable set we can just do here. So okay, so how can we describe stable set? Well, it's, as we said, it's integer points in where every coordinate is indexed by a vertex of your graph. Then first of all, you want to restrict to 0, 1 vectors, so the first thing is obvious. You will write down some linear inequalities which restrict every entry of your variable to be between 0 and 1, which means that, okay, it's a 0, 1 vector. So that's easy. And then for stateless sets, there are some obvious constraints which say that for every edge in your graph, yeah, let's say VW in your graph, you just have the requirement that you can pick at most one of V and W. So XV plus XW is at most one. Right? Now it's easy to see that the 0, 1 points, or the integer points in that set, they're precisely the characteristic vectors of stateless sets. Does that make sense? Very basic, right? So let's do TSP. That's a bit more challenging. So again, I'm talking about the undirected graph, and I want to model Hamiltonian cycles in this graph. So there are different formulations. The most typical one that you find in most of the books is the following. Again, we have integer points in the edge space now. Again, every edge, every value should be between 0 and 1, so that's fine. Now, the first thing that comes to your mind is that, well, I mean, I want to describe cycles, so every node should have degree 2. So the compact form of writing this is the following. So by this I mean this is the edges incident to V, right? And by x of this, I mean sum up the values of x of these things, right? So this says that every vertex must have degree 2. But now you have the problem that if you just leave it like this, you model like a disjoint union of cycles, so, but you want a second cycle, like a single cycle. So one typical way of dealing with this is saying that for every subset of the nodes, which is for every non-trivial subset of the vertices, you say that you want at least 2 edges leaving the set. Right? Again, this is like all edges that leave S, and here you sum up the x values of all these edges. So it's a linear inequality as well. You agree so far? Very good. Good. Very explicit. Now, the downside of this formulation is that it has exponential size, right? Because I'm writing down such a constraint for every single subset S. So that's bad. That's nothing you want to put into your solver if, you know, you want to solve TSP for even hundreds of vertices. That's not what you want to do. So that's why, yeah, usually people come up with different formulations. And one other formulation, I think I prepared it here, is this one. Don't be scared. We don't need to understand all the details, right? It's not about this specific form, but it's a very famous like approach. So if you look at so this is an alternative one, okay? So if you look at the first row, that's exactly what I wrote before. X is between 0 and 1, and all the degrees have to be 2. And now we want to replace these exponentially many constraints by hopefully fewer ones. Okay? And the common approach is to somehow enforce the fact that you fix, so what you do is you fix a node S in your graph, right? And then you know that in a Hamiltonian cycle, for every other vertex, let's say T, we know that there exists 2 paths going from S to T, right? Or in other words, in this LP world, we like to talk about flows. So there should be a flow of value 2, like sending 2 units from S to T. And this holds for every T. So what we do is we fix S. And now if we want to talk about flows, you should bidirect everything. So that's what I mean by E prime. So let's bidirect everything, okay? But again, it's not about the details. And now what you say is, for every vertex T that is not S, we introduce some auxiliary variables, yt. So this is a set of, like a bunch of variables on the directed edges, and they should model a flow, right? So this says that for essentially for every vertex, what goes in should be equal to what goes out. And in total, I want to send 2 units, okay? And now I want to connect these 2 types of variables. I want to connect y and x in the obvious way, which is whenever y wants to send a unit along an edge, the x variable should jump to 1. That's the idea. You don't have to, like, let's not look at all these constraints in detail, but that's the idea. That's what you do.
So this I'm a bit slightly confused. For any ST, you want to define a flow, right?
You could do this for any ST, or you could say, okay, let's fix one S. And now for every T, you want to model a flow from this fixed S to that T.
So the YT is
YT is a vector of variables. For every T,
vector of variable.
for every T, YT is a, like, think of it as a full flow that has a value for every edge. But I have several flows, right? Yeah. So this is very typical in integer programming. You see such formulations many, many times whenever you want to express connectivity. That's very typical, right? And the good thing is this is all linear constraints. That's all fine. And the good thing is that if you now count the number of variables and constraints, now you see that, oh, this is polynomial in the size of my graph, right? Whereas this was exponential. However, this formulation somehow conceptually has a difference to this formulation because it uses auxiliary variables. Right? We're not only formulating things in terms of the original variables, we're using auxiliary variables, which is very typical. And the fact that we found a polysize formulation for TSP in this case is not very surprising. It turns out that whenever you give me a reasonable set X, and by reasonable, I mean, it can be very, like, even if deciding whether a point, a 0, 1 point belongs to X, even if this problem is only an NP, so a very weak requirement, even then you can always find the polynomial size description like this, which is, it follows from what does it mean to be an NP. So the existence of a polysize formulation is not that surprising, okay? But of course, usually you will use auxiliary variables. Whereas for some other problems, which are also NP-hard, let's say, like stable set, we didn't use any integer variables. So the question that we asked several years ago, more than 10 years ago, was the following. So in which cases is it really necessary to use auxiliary variables, in addition to the original variables, to obtain a small size formulation in terms of an integer program? Right? So that's a question you might ask. Well, that's what we did. What did make sense? And for this reason, you may want to introduce the following notation to formulate this a bit more formally. So for a set of integer points, you can ask this for general integer points. Now, every system in the original space that defines some linear inequalities, it actually defines a polyhedron, right? So the polyhedron is just the set of all points satisfying these inequalities. That's what we call a polyhedron. So a polyhedron, polyhedron P in the same space as X is what we call a relaxation of X if, well, if the integer points in P are precisely those of X. That's, if we don't want to use any additional variables, that's exactly what we're looking for. A polyhedron so that the integer points in the polyhedron are exactly those of X. And now we're asking, okay, like how many inequalities do we really need for such a polyhedron so that it's a relaxation of X? And this motivates the following definition, which we call the relaxation complexity. That's the relaxation complexity of X, which is the minimum number of facets. So if you don't know what facets are, that's the inequalities you need to describe P. The minimum number of facets of a relaxation of X. That's the relaxation complexity. Let me know if
you stay in the same dimension. You don't
yes,
increase dimension.
yes, yes, right? Which is nothing that really an integer programming solver cares about. I mean, right? So this is not really a practical consideration. It's more like a conceptual one, right? So why do I need X? Like, Why is it so easy for stable set, for instance, and is it really hard for TSP? No, I don't know. Yeah, so for instance, if you now translate this question to TSP, the question that we're asking is, what can we say about the relaxation complexity of, well, the relaxation complexity of X step, it's polynomial. It's actually linear in the graph, right? We've seen this. Okay. The more interesting question is, what about TSP? Right? And let's say here the graph is really the complete graph. Okay. So what is the relaxation complexity of TSP? We know that it's at most exponential, like it's at most this. Like we know one relaxation, definitely, that does the job, is exponential. Right? And now the question that we're asking, I mean, maybe there is a completely different formulation in the original space that is smaller, right? So that's what we're asking.
Can I ask a question?
Yeah.
I think I still don't understand the connection between the way this relaxation is defined and the auxiliary variables. Like,
Yeah, so the way you should think about this geometrically is, so think about you have some integer points in the plane. Right? So suppose that's the plane. That's the integer points that you want to describe, and maybe there's a bunch of integer points you don't want to describe. Then a relaxation is really an object in the same space, like something like this is maybe a relaxation.
exactly.
Right?
Yeah.
But if you use additional variables, you go to a higher dimensional space, and somehow the way you should think about this is, it's like an object in a higher dimensional space that somehow projects down to a relaxation.
But where is the number? The number of auxiliary variables is now the new dimension in which you.
That would be the new dimension, but I'm not allowing, like in this concept, I'm not allowing additional variables.
This thing in quotes, I thought this was about writing an ILP with as few auxiliary variables.
Oh, I see. Yeah, maybe I should have been more specific. So I want to understand if I don't use any integer variables at all, if I just stick to the natural original variables, can I also come up with a, let's say, small size formulation for TSP? When do I need additional variables? That's the question. Yes, and so the first thing I would like to discuss is what is this? Is this exponential or is this polynomial? That's what I would like to discuss. But let me know if this sounds weird to you.
So this is is it like the usual way I would want to relax an ILP to an LP?
Yeah.
And then so at least in the usual, and of course in the usual way, it's not clear if this polyhedron, if the polyhedron of the LP, no, this is no, yeah. If the usual way is I allow non-integer, non-binary values of x. I look at that relaxed.
Yeah, when people go to LP relaxations, that's what they allow. At some point they forget about integrality, because solving an IP is difficult, so let's first solve the LP and let's hope that it still gives me something reasonable. Yeah. But whenever you write down an LP, you make sure that it might be loose, it might not be a perfect description for the convex hull of what you do, right? Yes. It's usually something that is more loose, right? But what you usually make sure in all these formulations is that it at least contains the right 0, 1 points. That's how you usually write down your model, right? And that's exactly what a relaxation is.
Yes.
Yes.
So it's the same relax. Is it different from an LP relaxation? I think that's
no. That's if you want to call it an LP relaxation, that's why I call it the relaxation.
And then I'm trying to understand this term, minimum number of facets. You said
facets is inequalities, number of inequalities.
When I do a usual LP relaxation, the number of inequalities are not going to change from the given ILP relaxation.
That's true. That's true. But you agree that a certain problem might have many different relaxations. Right? So, I mean, I agree that it's somehow natural to write down these constraints. But in which sense are they like the constraints you have to write down? There's no geometric, like,
So is it the same as just writing an ILP with as few constraints as possible? Is this the same
yeah,
as
it's the
RC?
same question.
Okay.
Yeah,
Okay.
yeah. And the only thing to keep in mind is that, I mean, what I want to convey to you is that in some situations, that's what people do in practice. Sometimes it's really hard to express a certain condition, like some certain logic, if you just stick to the original variable. Sometimes you would naturally use some auxiliary variable, that, I mean, without thinking about it, right? But we were conceptually thinking about, like, when do you really need additional variables to express something? And it turns out, and so that's what we thought about. So what can we say for TSP? Do we need these exponentially many constraints if we refrain from using auxiliary variables? And the thing that we could prove back then with Volker was that this is in fact exponential. Okay? Like whatever you do, whatever fancy other constraints you come up with, you will always use exponentially many constraints. Okay, so does the result make sense? Okay. And the cool thing about this result is that it has a very simple proof. I mean, it took us a while to find it, but now in the end it's very simple.
But doesn't this contradict with my alternate definition of RC?
No, it does not.
Because
Give me a poly-size formulation for TSP with a like LP relaxation that does not use additional variables.
earlier I said I'll just give you an ILP.
Give
for
me
TSP, one. That's the ILP I give you.
There's a
No, but that's additional variables.
Yeah, because earlier I said I'll just give you an ILP for TSP. I didn't talk about additional variables, so that's not.
Yeah, that's the difference. It's really,
I
this
agree.
is, I'm not allowing additional variables for the moment.
Okay. All right.
That's, yes, so this is, so that's the first result, like a nice one. So, so let me try to present a simple proof to you. That's the first proof I would like to present. And it's very combinatorial, it's very easy. You don't need to understand anything about polyhedra or whatever, or about relaxations. It's very simple. So suppose we have a set y of integer points which do not belong to the set that you want to describe. For the moment, let's not care about which points we want to describe. Suppose you have a set like this, such that with the following property, such that whenever you pick 2 points from this magic set y, which are distinct, suppose that you choose them in a way that whenever you take 2 points and look at their line segment, the convex hull of these guys, then it will intersect the convex hull of X. So what I mean is that suppose this is your set X, right? And now I might give you this set Y, right? Now you see that, okay, we're talking about the convex hull of X, which is this thing. Now this set Y, well, no, maybe not. Okay, let's be safe,
Yeah.
right? Because, right, you see that whenever I pick any 2 points I pick, their convex hull crosses this, right? Good. So you might think of it as like a certain graph, and it's click, whatever. Anyway, right. Then my claim is that if I can find such a magic set Y, then it automatically means that the relaxation complexity is at least as large as Y is. The reason is very simple. Suppose we have a relaxation. I mean, this relaxation, it must separate the yellow points from the white points, because they do not belong to X. But any linear inequality of my relaxation, it can only separate a single Y point. You can never separate 2 points, because then you would intersect the convex hull.
I see.
Very Very basic, right?
Yeah.
You agree, Tony?
I agree.
Good, good, good. Right. So now, the only thing, I mean, that's a simple idea. The only thing we have to do is we have to find a nice set Y, like a yellow set for TSP. That works for TSP. And that's why I brought some hamburgers. Okay. I'm from Munich, not from Hamburg, but you will be happy. Good. So what is this? So this is 2 points from my set Y. Maybe that's Y and Y prime. So how do I construct them? I mean, they are 0, 1 points, so they belong to some graph, right? So the way I construct these graphs is the following. So I have these blocks here, and you know, we're surrounding them by the buns, right? And now for every block, I can decide whether I go like parallel or whether I choose to cross. Okay? Now the only rule, like I tell you, you can do whatever you want. The only rule is the number of crossings you must have should be an even number. And all the hamburgers you can obtain in this way, that's my set Y. So let's see. I mean, since they cross an even number of times, you see that this is certainly not a Hamiltonian cycle. It's actually it's 2 cycles, right?
Mm-hmm.
Same for this guy. So these two guys, I mean, it makes sense. That might be my set Y. And now I claim that it's very easy. Now I claim that this set Y has exactly this property. What is the property? Whenever I take any 2 points, let's take these 2 guys, I need to show that their convex hull intersects the convex hull of the TSP points. And in this, usually understanding the convex hull of TSP points is absolutely complicated, but in our case it's easy. Because what I do is, I look at 2 other hamburgers. Okay, so these are even hamburgers, and these even hamburgers I slightly twist to make them into odd hamburgers. Right? X prime.
Nice.
And what I do is, I mean, these hamburgers are different, right? So what I do is I search the first position where they differ, which is this part, right? So this part, here's parallel, and this part here's a cross. Let's just change this. So both become odd, right? That's exactly these 2 guys. Both become odd. And if it's odd, then it is a Hamiltonian cycle. So they belong to TSP. But now by this simple, you know, swapping argument, this means that if you look at the midpoint of these 2 points, is exactly the midpoint of these 2 guys. So if you take 1/2 of this vector plus 1/2 of this vector, this is exactly the same as this thing, right? And that's it. Clean, simple, and of course this family is of exponential size. I have exponentially many points in Y, so the relaxation complexity is exponential. Very good. Half an hour, perfect. Great. Yeah, so this is things that we studied back then. And you obtain some bounds for other sets as well, etc. Very good, very good. Yeah, let me clean. Ooh. Oh yeah, there it is. Actually, I have exactly the same in my office. Ooh, nice. Good. Can I erase this?
So is this same for TSP on any graph? Or?
No, for some graphs, I believe no. Like if you have very simple graphs, it's
Okay.
yeah. So this is very specific. But usually people formulate TSP on complete graphs because you really imagine you have a distance between any 2 cities. Yeah. I don't have any interesting results on like special families of graphs.
But as long as these hamburger graphs are subgraphs, then
Absolutely.
yeah.
Yes. Yes. Right.
Does it matter that you're assuming an even number of vertices? I mean, I suppose that's not as.
No, I mean if you have an odd number of vertices, like
You can
I mean we can certainly somehow include it, like it's here.
Okay.
Yeah.
maybe it might be interesting if it's still hard when the graph is planar.
Oh yeah. 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 I would somehow. assume that there is also a construction. But, yeah, that's a good question. That's a good question too. All right, good. So that was to get familiar with it a bit, and yeah, we have seen one proof already. So when we studied this concept back then, of course, I mean, when you first study a concept, of course, you ask lots of basic questions, because many things weren't known before this. And I guess a natural question is, okay, what is actually the relaxation complexity of some very basic sets? Like TSP is quite complicated, like some very basic sets. And it turns out that there's actually only very few sets X for which we really know the relaxation complexity. So let's maybe start with like a very basic set. Let's do really the set of all. Now it's becoming really esoteric, but let's do this. Okay, let's do this set, right? But yeah, that's the discrete math group, so I'm allowed to talk about it. Right, so that's the points we want to describe. And of course, the usual way to describe these points is just let's write down these 2D inequalities, right?
Yeah.
Why not, right? And there, in practice, there's good reasons that you write down exactly this and nothing else. So all it says is obvious. Is certainly it's at most 2D, right? But I guess already in 2 dimensions, you see that I can save one inequality by carefully drawing something like this, which is not right. It's not surprising. But we can do this in dimension 2, and actually you can do this kind of. You can always find like this tetrahedron or a simplex thing. So it's not hard to see. Like it's pretty easy to see that. In general, like you can use a simplex to do this. It's at most d+1. Okay, good. Right. But let's think about this. Like, can we do better? Yes, question to you. Can we do better, or is there anything suspicious that comes up?
Would it not be bounded?
Very good, very good. Right? In dimension 2, we see that if you use only 2 inequalities, I mean, this thing becomes unbounded, and we get infinitely many integer points. I mean, that doesn't work, right?
I see.
And so that's a fact. But we need to be like any d-dimensional polyhedron in order to describe a d-dimensional polyhedron. In order to get it bounded, you need at least d+1 inequalities. Everything with less is unbounded. Okay, unbounded, good, fine, but unbounded suggests that if it's unbounded, you will collect many integer points that you don't want, right? And in terms of the cube, in terms of this, you can play exactly this argument. There is an unbounded direction, then you might use something like Minkowski's first theorem, whatever. Things that, oh yeah, you will find infinitely many integer points because this guy is so large. Okay? So it turns out that, so this is a fact. In this case, you can prove that you cannot do better. It requires some careful arguments, but nothing too deep. So this is, here we know this. Okay? Very good. Right. Now the object that I would like to get to is, let's say, maybe the second most natural set of points you would like to describe, which is what we usually call the standard simplex. Let me give it a prime because I will use delta d for something else later. So, which is, it's arguably the simplest d-dimensional set of points that you can think of. So it's the unit vectors together with, like the standard unit vectors together with the all zero vector. I hope you agree this is also a quite basic set, right? Mm-hmm. Yeah, this is the usual relaxation. Something like this. Then, so usually the way you describe this, also like this kind of thing you describe very often in certain integer programs, whenever you want to say that, oh, among some binary variables, at most one can be chosen. So it's a very natural thing that you model all the time. How do you do this? Well, you write down non-negativity constraints for all of your variables, and then you have a single constraint saying the sum of all xi is at most 1. So this gives us d plus 1 inequalities. So certainly delta d prime, that's relaxation complexity is at most d plus 1. There you go. Now the question is, can we do better? Again, you might play the same game. You might say, well, I mean, if I use fewer than d inequalities, I mean, this thing is unbounded, right? And we could use this argument and show that, okay, like, in fact, this is d plus 1 for, yeah, only in small dimensions we could show this. So what comes now is very counterintuitive, but yeah, welcome to higher dimensions. So we could prove this, okay? So you cannot do better in small dimensions. In fact, which in 2 dimensions that doesn't seem to be surprising. And now, oh yeah, and we tried to prove at least some lower bound, and at that time I think the lower bound we could prove was something like log d over log d, something like this. And later Averkov and Schymura, they improved our construction. I think this is from 2020. So they showed that, okay, you cannot do better than like really logarithmic. Like this is, but they weren't able to improve this bound further. And even more surprisingly, okay, so who is it? I think I should start with Manuel, Aprile, Averkov, Summa. Oh yeah, and Hojny. 22, I think. They proved, surprisingly, that this is not anymore true in dimension 5. Okay, so, oops. So you would think it's 6, but it is 5. But the more dramatic thing is that in higher dimensions you could really even go down from linear. So it's O of d over square root log d. So you can really save something. And the weird thing about this is we said that if you want to go below d plus 1, I mean, you get unbounded directions. And now you have to be careful, because if the description you're using, let's say, only uses rational numbers, then basic polyhedral theory tells you that also these directions, you will find rational directions. But once you find an unbounded rational direction, again you can play the game and say, you will have infinitely many integer points. Which means that if you want to come up with a better formulation than this, you need to use irrational numbers. Okay? And that's what they did in a fancy way. It's a quite complicated construction. Okay? And yeah, I must admit, no, this is on video, but I never really understood the construction, so I didn't look at this for quite a while. And very recently, I don't remember exactly how, but we started thinking about this again. And
for the dimension 5, you're saying this is equal? So meaning
yeah. You can prove that you cannot do better than 4, not do better than 5, but yeah, the important thing is that it's not 6.
And also over there, there's equality as well?
No, this is really like O. Yeah.
Oh,
So at the moment we really have a large gap still between, right? So the lower bound is log d, and the upper bound is, well, just a little bit less than d. Yes, but good question, because that's exactly the gap that we're closing. So what we can do is we can prove that this thing is, well, now it's theta log d. Yeah, so you can really go down by quite a lot. By the same arguments as before, of course, this construction also uses irrational numbers. So that's nothing that you would use in practice to describe this thing, but yeah.
Can I ask what kind of constants you have here?
Oh, we will see it. It should be something very, yeah, now I'm bad with a, yeah, now we use the master theorem. We will see that the recursion is,
It's okay.
if you double something, you get a +4, whatever that means. You know. Yeah. Very mild, yeah, very explicit construction actually. Yeah, so for the remainder of this talk, I think I have the time. I would like to also give you the proof for this because it's also, in hindsight, it's also simple. I should say that we first found this proof, Simon and I first found this proof. We put the paper in archive and then we wrote, of course, these colleagues like, oh, you might be interested. And then Gennady Averkov had several very, very interesting comments about our construction. And actually, he was able to simplify it quite a lot. So now it was cute before, I think, but now it's super cute. So that's why now he's also one of our co-authors. Right. So let's do this. Let's prove this. We do this in 2 steps. The first step is actually delta d prime. That's why I call prime. It's not the nicest object. What I don't like is that the 0 vector is in there. That makes it a bit asymmetric. So that's why I will look at delta d, which is really just the set of only the unit vectors. And it turns out that, let's not discuss this in detail, but it turns out that if you know how to relax this guy, you also know how to relax the other guy. So if you want a relaxation for this, just take a relaxation for the d+1 guy and set some variable to 0 and you get one for this. Just believe me this, it's believable. And also, we use the fact that the relaxation complexity is monotone in D. Right, so if you have a relaxation for D = 7, just set the variable to 0 and you get one for D = 6. It's very easy. Good. But in view of this, what we have to do is we just have to prove the following lemma, which says that the relaxation complexity of this guy is at most the relaxation complexity of this guy +4.
Can I ask a silly?
Yes.
That is monotone, but the RC delta prime D is not.
Is also monotone in D.
What does that mean? Because you just showed that for higher values of D, the value is less than.
Yeah, I mean.
The constant here is hidden constant.
Maybe in the yeah. I mean.
Okay.
Yeah. It's yeah. Algorithm, yes. Up to constant.
Okay.
Good. So yeah, let's prove this. Right. So if I have a relaxation for the d-dimensional guy, I can get one for the one with double dimension by just spending 4 more inequalities, and this gives us the logarithmic. Very good. So here's the construction. So proof. Well, I told you we need to use irrational numbers. Actually, we need very irrational numbers. So what we do is we take some numbers, alpha 1 to alpha d, that are algebraically independent over q. So these are real numbers. They're algebraically independent over q. So the only linear combination of these guys with rational coefficients that brings them to 0 is the trivial combination. Okay. And so just as a notation, let's say f of x is just, so whenever you give me a d-dimensional vector, by f of x I just mean that take the linear combination of x with exactly these coefficients. Right? And also something else that will be useful is, let's say sigma of x is just a shorthand notation. Well, this is already short, but this is a bit more convenient. It's just the sum of the coordinates in x. Right?
Okay.
Good. Right. Now here's the descriptions. Like, suppose that p, suppose that P is a relaxation for delta D. Suppose we already have one, let's say with K facets. So we pick a small relaxation for delta D. Now what I do is, here's a relaxation for Q, I claim, for delta 2D, which is, okay, now it should correspond to vectors in R to the 2D. Oops. Let's call the first part X, the second part Y. And what do? I will require that X plus Y is in P. And I will add 4 more constraints, which look a bit fancy. So I'm saying that, okay, X plus Y should be in P. And moreover, the absolute value of f of X should be at most m times sigma of X, where m is a sufficiently large constant. Like in interprogramming, people call this big M. Like, use some sufficiently large number. We will see what is the meaning of these two guys. Note that this is this you can write as 2 linear inequalities, each of them. So this is just 4 more. I have those inequalities that were already in P, plus 4 more inequalities. And now I have to prove to you that Q is like the only integer points that are in Q are precisely the unit vectors. Good. So first of all, like this has K plus 4 facets. Sorry. Yeah, we only add 4 inequalities. And it's also, it should be clear that delta 2D is a subset of Q. Right? We want to show that the only integer points are precisely those, but this is clear, right? Because, so what is this? Well, it's the set of all unit vectors. Take a unit vector, right? So it will like split its components. Of course, its sum will be again a unit vector, right? So if you, right? If it like looks like this, then this plus this is still a unit vector. So this thing is certainly in P. And this is trivial. It's like, I mean, the sum of its entries is 1. So if I make m big enough, then this is certainly satisfied. But that doesn't do anything yet. So now we have to do the opposite direction. Okay. So let x comma y be an integer point in Q. And now we have to show that this can only be a unit vector. So maybe let's call this constraint 1, 2, and 3. By 2 and 3, we know that sigma x and sigma y, so the sum of their entries, the sum of the entries of x and the sum of the entries of y, they're both non-negative, trivial reasons. They're both non-negative. Right? Very good. And don't worry, proof is short. We're almost done. By the first fact, we have that the sum of these two numbers, well, it's, I mean, I could also say, well, it's the sum of all entries in x plus y. Well, this point is in P. P only consists, like, it's an integer point in P. So its sum of entries is exactly 1. So this is 1. So what is this? We have two non-negative numbers whose sum is equal to 1. So this means that there's only two choices. So sigma x and sigma y, they're either, well, 0 and 1 or 1 and 0. These are the only two possibilities that these two numbers can have. Right? So now let's just look at this case. This case is symmetric. We can finish. So if sigma of x is 0 and sigma of y is 1, then from this thing, and now this is exactly the purpose of these weird looking constraints. If I know that sigma of x is 0, I know that, oh, the absolute value of f of x is 0, so f of x is 0. But since I chose f of x to be this linear combination of algebraically independent numbers, the only way to make this 0 is that all entries of x must be 0. That's the trick we're using. This is the... So this will imply, by the algebraic independence of the alphas, this will imply that x is all 0. Right? Good. And now why are we done? Well, now you look again at constraint 1. So we have already learned that the x part, that's entirely 0. So this sounds good. Now we just have to show that y is a unit vector. So why is that? Well, y is now equal to x plus y because x is all 0. But we have learned that x plus y, I mean not learned, that's a part of the definition. This thing is in P. So that's an integer point in P. But P was a relaxation of the standard simplex, or the probability simplex. So the only integer points in here are unit vectors, so y is some unit vector. That's it. So maybe, I mean, I hope you agree that the proof is short. Maybe it was still a bit too fast at some point. But all you like maybe the takeaway is, maybe that's a trick you want to use at some point, I don't know, is perhaps this one, right? With algebraically independent numbers, you can force something whose evaluation is 0 to 0. And that's what we exploit here, and so...
But why exactly did you need this irrationality, the algebraic independence over Q?
Because I mean, if you just tell me that such a sum is 0, I mean, maybe x has some negative entries, some x have negative entries, some have positive. I mean, this might still add up to 0, although this is not the 0 vector.
Yeah, but you needed irrationality for that. You could have just gone to some positive, let's say positive rationals or something like that.
No, the thing is that I like nobody tells me that these xi's are non-negative.
Okay.
Right? Because this is, unfortunately, I can't enforce this because this is too expensive. This would require me to write down d linear inequalities. But that's exactly, like, we have to circumvent this somehow with this trick. Yeah. All right, that's it. Thanks a lot.
Very nice. Any questions? Yeah.
Do you think a similar construction would work for if we define some relaxation complexity in numbering with some algebraic number field? Because all like the core part we use is algebraic independence.
Yeah, the thing that I'm missing here, but yeah, probably because it's a long time ago, is that I mean, in order to talk about relaxations, you need this notion of linear combinations of, like, you need this notion of linear inequalities. So you need to be in some ordered field, I guess. Yeah, so in that sense, I don't know what it would mean. Yeah.
So for practical purposes, maybe nobody want to use irrational coefficients, right?
Definitely.
So if you restrict the complexity to only the rational
rationals.
coefficient, then do you have a...
Yeah, then going, as I said before, then going to unbounded things is not an option, because if everything is rational, and you're unbounded, there will be a rational unbounded direction,
Mhm.
and you will collect tons of integer points.
Mhm.
And moreover, to be fair, I should really say that in practice, right? So now let's. So this is really an impractical notion, right? Because in practice, what you really do is, so that's the general advice. If you have a set of integer points, and you know exactly how to describe its integer hull, then do it. If it's not requiring too many inequalities, because an integer programming solver in the beginning it will just solve the LP. It will greatly benefit from the fact that you start with something that's very close to it. So usually in practice we start with something like which is a bit larger because we don't know exactly how to describe this, but try to be as close as possible. A solver wouldn't mind between, whether you use D or 2D inequalities. That's not like, try to be as tight as possible. Yeah, that's the practical advice. Yeah.
So I guess there is also like relaxation extension complexity,
Yeah.
where I allow you to use extra variables for the IP.
Yeah.
I mean, are there natural problems that like you still have exponential relaxation extension complexity?
No, because like really this power of having integer variables, but also having the power of projection, like the extended formations. This like lets you describe everything. Like by what I said before, like if you have a polynomial algorithm to just recognize whether a 0 point is feasible, right? In this case, you will always, take that Turing machine or whatever and turn its circuit into a formulation. So, yeah, I don't know of any problem that has exponential extended relaxation complexity because it would be weird, a weird thing.
So what is going to be the definition of extended relaxation complexity? You add D variable, you K variable, and then
You can use extra variables, and you have integer constraints as well. Right? So like TSP has polynomial.
Yeah,
like,
I mean the concept absolutely makes sense. It's just that it's a very powerful concept. That's, yeah. Hard to prove lower.
do you have some open problems, like some
Oh
cases
yeah,
where
it
it's
would
unknown?
be nice to pose some open problem. No, probably due to the fact that this is quite new. No, I don't have a good open problem on this at the moment. I should think
Maybe
about it.
off the record, maybe. Yeah.
Bad open problems.
Yeah, even this.
Yeah.
I don't know.
Any other questions?
And do you know if like a +4 could be improved at all? It seems like maybe not, but
Yeah. Yeah, I think our student, I think Simon has looked into something. Yeah, for optimizing constants, not like in this lemma, but you could replace it also by a slightly different lemma. I think you can. Yeah, now I remember. I think this would give a constant of 4 somewhere here, and I think he can do it with a 3 point something. But I haven't looked into it actually. Yeah.
I see.
But now this, to be honest, this is not anymore my business. Like this, I'm happy with asymptotics.
Can you that probably doesn't improve anything, but like you could do it several times with like x plus y plus z, but
Yeah.
no, that gives exactly the same function, right?
Yeah.
You will have divide by 3 plus 6.
Yeah, I have to check my emails. Like he sent me something like, no, you can optimize the constants, but yeah, I was distracted. But I'm sure you can do something. Not clear.
All right, any more questions? Okay, if not, let's thank the speaker again.